You ever stop and think about how the internet actually works? I mean, really works? We're going to pull back the curtain on one of the key pieces of that puzzle, OSPF. Seriously, you can just think of it as the GPS for all your data. I mean, just think about it for a second. You hit send on an email, right? And boom, it just flies across the globe, bouncing between who knows how many routers, cities, maybe even continents, and gets there in a heartbeat. That's not magic, folks. That is some seriously clever engineering.
And a huge part of that clever engineering is OSPF. That stands for Open Shortest Path First, and it's exactly like the GPS on your phone. You know how your phone looks at all the roads, checks for traffic, and finds you the absolute best way to get where you're going? Well, OSPF does the exact same thing, but for your data. It's what makes routers smart enough to pick the fastest, most efficient path every single time.
All right, so here's what we're going to cover. First, we'll dig into that whole network GPS idea. Then, we'll see how routers literally make friends with each other to build a map of the network. From there, we'll check out how they find the fastest route, handle enormous networks, and wrap up with why OSPF is, well, such a dominant force.
Okay, first up, the network's GPS. So the thing you got to know about OSPF is that it's a linked state protocol. And that one little detail, well, that's what makes it so incredibly powerful.
And the difference is huge. See, older protocols were kind of like driving by asking for directions at every single intersection. They only knew the very next turn. But OSPF? No. OSPF gives every single router a full, complete, real-time map of the entire network. Think about that. With that map, every router can see the whole picture and make its own smart decisions about the best way to go.
But, a router can't just start sharing maps with total strangers. First, it has to introduce itself to its immediate neighbors. It's a whole process, kind of like a formal digital handshake.
So at first, a router is in what's called the down state. It's basically just listening, hasn't heard from anyone. Then it sends out a hello packet. When another router hears that hello, it goes into the init state. But here's the magic moment. When both routers see their own name, their own ID in the other's hello packet, that's when they hit the two-way state. They've officially become neighbors.
And let me tell you, OSPF is picky about who it becomes friends with. This is not a casual thing. For two routers to become neighbors, they have to agree on a whole checklist of rules. They have to be in the same area, use the same timers, have the same security, the whole 9 yards. And these rules are absolutely critical because they make sure the network is stable and that everyone is literally on the same page when they start building their maps.
Okay, so our routers have done their handshakes, they're officially neighbors. Now the real fun starts, building that complete network map. And the ultimate goal here is for every single router in the area to have a perfectly identical map, which in OSPF speak is called the Linked State Database, or LSDB. Now, this is where OSPF gets really clever in how it avoids total chaos. Imagine you have a bunch of routers all plugged into the same network switch. Without some rules, it would be like a room full of people all shouting at each other at the same time. Every router trying to update every other router. It's a mess, and it would crush their processors. So OSPF does something brilliant. It holds an election and picks one router to be the boss, the designated router, or DR. Now, instead of everyone yelling, all the other routers just talk to the DR. The DR then neatly passes along the updates to everyone else. This simple election cuts down the noise dramatically and helps the network get stable way faster.
And the way they actually share all this map info is, well, it's like a very polite, structured conversation. It's not just one big data dump. First, a router says, hey, here's a quick summary of my map. The other router looks at it and goes, oh, okay, I'm missing this part. Can you tell me more about that? Then the first router sends over the specific details. And finally, the second one says, got it, thanks. It's this super reliable back and forth that guarantees everyone's map ends up being a perfect match.
So what's the end result of all this? The big takeaway. After all the handshakes, elections, and polite conversations, every single router in an area has an identical linked state database, an absolutely perfect synchronized map of the network. And that map, that is the foundation for everything else.
All right, so everyone has the map. Now what? Well, now each router has to use that map to figure out the best way to get to every other destination. This is where the shortest path first part of the name really comes into play.
So how does it decide what the best path is? It uses a very simple metric called cost. Just think of it like this. Cost is the price to use a certain road. A big, fast highway has a very low price, a low cost. A slow, bumpy back road has a very high price, a high cost. It's all based on bandwidth. The faster the link, the lower the cost.
And OSPF is a bargain hunter. It always looks for the path with the lowest total cost.
And this chart really shows you what I mean. Look at that. A fast 100 megabit link has a super low cost of just 1. Drop down to a 10 megabit link and the cost jumps to 10. And man, look at those old slow links. The cost just goes through the roof. This is exactly how OSPF tells the difference between a superhighway and a dirt road.
Okay, so this is where it all comes together. Each router has the map and it knows the cost of every single link on that map. So it runs this super famous algorithm, Dijkstra's shortest path first. You can think of it as a superpowered calculator that sits there and adds up the total cost of every possible path to every single destination. And once it's done all that math, it builds its own personal set of directions using only the absolute cheapest, lowest cost routes.
Now, this system is fantastic, but you might be thinking, what happens when the network gets gigantic? I'm talking thousands of routers. If every single router had to know every tiny detail about every other router, that map would become impossibly huge and complex. Well, OSPF has a brilliant, elegant solution for this problem. It's called areas.
This analogy nails it. You wouldn't try to memorize every single street in a huge city, right? Of course not. That's insane. You know your own neighborhood like the back of your hand, and for everywhere else, you just need to know how to get to the main highway.
And that's exactly how OSPF areas work. A router knows every single detail about its own local area, its own neighborhood. But for distant areas, it just gets a summary, a simple signpost that says, downtown is that way. And all these different neighborhoods connect to one central highway system called Area 0, the backbone. It's just a genius design that lets OSPF scale up to massive sizes while keeping everything fast and efficient.
So, let's wrap this up. Why is OSPF the king? Why is it the go-to standard for pretty much every big company's internal network? It's not just one thing, it's the whole package. A killer combo of speed, scalability, and pure rock-solid reliability. I mean, just look at this list. It's incredibly fast at reacting when something changes. We call that fast convergence. A link goes down, bam, the network has already found a new path. It scales up to handle thousands of routers, no problem, thanks to that area design. It's an open standard, which means it plays nice with gear from any company. It's got security built right in, and it's super efficient with bandwidth, because it only sends out updates when something actually changes. What's not to love?
So if there's one thing you remember, let it be this. Those older protocols, that's like trying to find your way with a crumpled old paper map. OSPF? That's like having Google Maps running on your phone, with live traffic updates. It sees the entire road system, it knows where the problems are, and it will always find you the best route.
And that really leaves us with one big question to think about. OSPF has been an absolute titan in networking for decades, all thanks to its brilliant design. But our networks are only getting bigger, faster, and way more complicated. So what comes next? What's the next generation of network GPS going to look like?